Now we can get into part 3, where we've done all the conceptual pieces. Now we can get into calculations involving strong and weak acids and bases. So a pretty lengthy, just calculational lecture here as far as going through different examples, reinforcing our methodology for approaching these types of questions as well. So first example is how would one prepare 600 milliliters of a solution having a pH of 1.8 from concentrated HCl. Concentrated HCl is 36% by mass. We have a density of the concentrated HCl to be 1.12 grams per milliliter, and the molar mass for HCl is 36.5 grams per mole. So knowing all that information, we should be able to calculate then how we would prepare this. And basically what we're trying to figure out is how much of the concentrated HCl do we need to create this solution that has a pH of 1.8. So that's really what the question is getting at. So the first thing that we need to do is now to kind of start to that methodology approach is to identify our acid or our base. And in this case we have HCl, and that is a strong acid. With that identification, now we can write our reaction. And our reaction here would just be our hydrochloric acid really just dissolving in water, not in an equilibrium process, but in a one-way process to generate hydronium ion and chloride ion. Oops. And so that's that notion of, complete dissociation. And that's stemming from the identification process that this is a strong acid, and as such it should then have complete dissociation. And what that means is that our hydrochloric acid concentration is actually equal to our hydronium ion concentration. So in this case, for step 3, this is just a conversion process. for strong acids. And so as a result, there is no need for an ice table. We'll simply solve, right, using dimensional analysis. So that's what we need to do, is we need to just really kind of now approach this as a dilution example, and we want to use our dimensional analysis to actually determine that. So if we go back to the question, we find that we have, some data here. The most important data that I see is the pH of 1.8, at least to start off with. pH is really important because that automatically gives you H3O plus concentration. We do have a measurement, which is the 600 milliliters of this solution that has a pH of 1.8, and then we have a number of conversion factors. Right, notice that all of these have two types of units, one in the numerator and one in the denominator. And so as a result, these are conversion factors. So as far as our process goes, we have, a couple of steps that we need to do in preparing. Step A would be to get to our hydronium ion concentration, and that would be equal to 10 to the minus pH. Remember, pH is equal to the negative log of my hydronium ion concentration. So I've rearranged that to solve for the actual hydronium. Part B then is going to be using the dimensional analysis starting with our measurement. So really what we want to have at the very end of the day is we want to have, the volume of the concentrated HCl solution. That's what we're actually looking for. And we could get to that, that volume via the conversions that we actually have. So if we start with our measurement, again, that's always the best place to start, is that we have 600 milliliters of the solution with a pH equal to 1.8. Well, I could apply the concentration of hydronium ion to determine, right, my moles of H3O plus. So that pH of 1.8 allows me to do that type of conversion, to take the volume, apply the molarity, and then we get moles of hydronium. Moles of hydronium is actually equal to moles of HCl. right? That comes from the fact that we have here a very strong acid. Once we have moles of HCl, we could get to mass of HCl by using the molar mass of the hydrochloric acid, right? That allows me to go from moles to mass. I could then apply my mass percent and get into mass of the concentrated HCl. And then the final step would be to apply then our density to get at our volume. So those are the steps, quite a few of them, right? We first have to do step 1 here with the hydronium ion concentration, and then we get to moles of HCl via moles of hydronium ion. And then once we're there, we can then use the molar mass to get to mass of HCl, use the mass percent to get to mass now of the actual solution, and then finally using the density get to our volume of solution and then answer the question. So for A, really this is kind of step 1, right? We want to get at the hydronium ion concentration by taking 10 to the negative pH. And so that would be 10 to the negative 1.8, or a value of 0.0158 molar in terms of my concentration of H3O+. So that's part A. And so now we can start with our dimensional analysis. And solve the question. So we can start with our 600 milliliters of the, we could say, dilute HCl. We have a pH of we have a molarity as a result of a pH to be 0.0158. So we want to get out of the dilute volume of HCl and convert to our molarity, and we should be very careful there. Apologize for putting that 600 milliliters. We should be in terms of liters, so 0.600 liters would be our volume of that dilute HCl. We then want to apply our molar mass of 36.5 grams of HCl for every mole of HCl. So that's step 2, getting into the mass of the hydrochloric acid. Then we can use our percent, that there is 36 grams of HCl for every 100 grams of the concentrated HCl solution. So getting out of mass of the solute and getting into mass of the actual solution for step 3, and now we're going to use the density of 1.18 grams of that concentrated HCl for every milliliter of the concentrated HCl. And so that is our 4th step. And we end up with a volume of 0.86 milliliters of concentrated HCl and then dilute up to 600 milliliters of solution with H2O. And that's how we would prepare this solution that has a pH equal to 1.8. So there is a strong acid type example. Let's look at another example, but maybe let's focus now in on a strong base. So we want to calculate the pH of a solution that's prepared by dissolving 8.5 grams of barium hydroxide in 750 milliliters of aqueous solution. So there's our question here. And so we want to find, kind of the same methodology occurring here. Step 1, we want to identify, the material. And here we have barium hydroxide. This is, one of our examples of a metal hydroxide, and this is an example of a strong base. That allows us to then write the reaction, and so really what we're looking at is just that simple dissociation, right? We want to have complete dissociation. And notice that for each 1 molecule of barium hydroxide, we actually get 2 moles of hydroxide. So our reaction here is complete dissociation. And that's a result, again, of the idea that we have a strong base. So we have complete dissociation. And that means from my barium hydroxide, I can then determine my hydroxide ion concentration. And we'll see that we'd have to have a factor of 2 there because of the fact that we have, 2 of the hydroxides for every 1 molecule of the barium hydroxide. So the 3rd step here, we don't need to go to the ice table again because it's strong. right? Since this is a strong base, we just need hydroxide so that we can get at POH, so then we can get at pH. So looking back at the question, we have the ability here with the 8.5 grams and the 750 milliliters of aqueous solution. That's allowing me to figure out my barium hydroxide concentration, which now gives me access to hydroxide. So those are kind of the steps that we want to do then, is really shown here with step 1 getting at our hydroxide concentration, step 2 getting at our POH, and then step 3 getting to the pH. So if we start with our mass, we have 8.5 grams of the barium hydroxide. Again, that's our measurement here. And if we divide by 171 grams, we can get into now moles of barium hydroxide. And then going one step further with the conversion between the molecule and then the specific quantity that we want, which is the hydroxide. Now with our moles of barium hydroxide converted to our moles of hydroxide, we can simply divide by our volume of 0.75 liters to get the molarity of the hydroxide, which is 0.132 molar. So that's really the first piece, right, is getting at that concentration of hydroxide. And then we can go to the second piece, which is to get our POH. Remember, that's the negative log of our hydroxide ion concentration. So that's the negative log of our 0.132. And we end up with a POH equal to 0.88. And then that allows us to get to step 3, which is now to get at our pH by taking 14 minus the POH. So we would take 14 minus our 0.88, and we get a value of 13.12. So that is a strong base example. Again, with the steps, first step, most important, identification. Once we identify it being strong, whether it's strong acid or strong base, that immediately tells us that we have complete dissociation, and now we can relate the concentration of acid to the concentration of hydronium ion in the case of a strong acid, or in this last example, we can relate now the concentration of hydroxide to the concentration of our strong base, barium hydroxide. Let's now move to the weaker side of the picture. So let's look at an example with a weak acid. We want to determine the pH of a 0.400 molar hypochloric acid solution. I'm sorry, hypochlorous acid solution. the Ka for our hypochlorous acid is equal to 1 times 10 to the -8th. So there's our question, and again, we want to start our methodology with, the first bit, which is we want to identify, the material. And here we see HOCl, which we might think is a strong acid, but we also have a Ka associated with it. Because we have our Ka, structurally it looks like it's inorganic, but because we have our Ka, that means we have a weak acid. So that helps us with our reaction, which has to be an equilibrium process. And that's again because of our weak acid identification, that our Ka is now telling us we have an actual equilibrium reaction. So we have to write that reaction. This is asking a little bit more of you as a student, right? We have to write our starting material. Remember, H2O is always a part of the process. And then we're generating hydronium ion by the proton shuffle, that hydrogen moving from the HOCl to the H2O. And then that means we get hypochlorite as the conjugate, or conjugate base in this case. And we have a Ka that defines the process. Our Ka would be equal to the hydronium ion times our conjugate base, the hypochlorite, all over our hypochlorous acid, and we have a value of that as 1 times 10 to the -8th. That's now setting us up for our ice table. So we have here the players within that equilibrium constant, our Ka. We have our hypochlorous acid, our hydronium ion, and then our hypochlorite. And we're going to be looking at initial change and equilibrium. So if we go back to the question, what information do we have? The only information that we actually have is that we have an initial concentration of our HOCl. Right? We've already used the Ka. We have that feature already, but that's the only type of information as far as our ice table is concerned, is that we have this 0.4 molar solution. So since there's no mention of pH or hydronium ion concentration or hypochlorite, the conjugate base, we have to assume that those are 0, and that's telling us our direction of change, that we're going to be increasing in terms of the product, decreasing in terms of the starting material, and since everything is 1 to 1 to 1, these would all just be simply X values. So we end up with 0.4 minus X for our hypochlorous acid. We end up with X for our hydronium and X for our hypochlorite. So now we can substitute back into Ka and solve for basically X, which equals hydronium ion, which then allows us to get to pH and solve the question. So our Ka is up there at the top. So we would have 1 times 10 to the negative 8th is equal to x times x in the numerator over 0.4 minus x in the denominator. So you find that we have, an upper level polynomial. Can we assume? And so here we have a Ka less than 1 times 10 to the negative 4th, and we have starting material concentration initial. So the answer to that question is yes. Right? We can assume x is small. So because of that yes, we can then get rid of that particular x. And so we have 1 times 10 to the negative 8th is equal to x squared over 0.4. We can then rearrange and solve for that. Right? We would want to have, our 1 times 10 to the negative 8th times 0.4. That's equal to x squared. And we want to take the square root of both sides. And we find x, remember, which equals our hydronium ion concentration, is equal to 6.32 times 10 to the negative 5th molar. We can then solve for our pH. And we get a pH equal to 4.19. We do need to do an assumption check. And so we would need to maybe do percent unchanged, or I'm sorry, let me do percent changed, which would equal x over HOCl initial minus x times 100. And again, we need to do that, right, because of our assumption motif, right, that we made an assumption, so now we need to actually check it. So our percent change would equal the 6.32 times 10 to the negative 5th over our initial 0.4 molar minus that value, and then times 100. And we end up with percent change equal to 0.012% change. That means that we have a good assumption. And so our answer is 4.19. If we had a bad assumption, right, where we would have something greater than 5% change, then we have to go back and do the quadratic. But here we're okay, our assumption is good, our percent change is way less than 5%. So we're okay with our pH being equal to 4.19. Let's look at another example and maybe start to solve for the other side of the equilibrium expression. So here in this example we have caproic acid. Caproic acid has this formula of CH3, and then we have 4 CH2 repeat units within our acid, carboxylic acid functionality on the end. Caproic acid is actually found in coconut oil. When we have 5.5 grams caproic acid in 500 milliliters of aqueous solution, the pH of the solution is 2.94. What I want us to do is calculate the pKa of caproic acid. So there's our question. When we dissolve 5.5 grams of caproic acid in 500 milliliters of solution, we get a pH of 2.94. From that information, we should be able to calculate the pKa of this particular acid. So our first step here is to identify. And we see with, our structure, our structure has that weak acid functionality, the carboxylic acid. So that's, one way to identify it is looking at that CO2H. But also, we're solving for a pKa, which is, basically a Ka just after we've taken the negative logarithm of that Ka. So both of these are telling us, again, we have a weak acid material in terms of this caproic acid. So that tells us our reaction. We need our reaction to be an equilibrium process because of that identification feature that we have a weak acid. And so we just want to show that migration of the proton. So the caproic acid is going to react with water. That is defined by our Ka. And we would produce hydronium ion and then capro8, which would be the molecule caproic acid, but now minus that proton. And so now it's a negatively charged molecule. And that is our conjugate base. So there's our equilibrium expression, which allows us to then write our equilibrium constant and what it is dependent on. Such as the caproate, and then our hydronium ion with our products, and then that's all over the caproic acid starting material. And we don't know our Ka, so that's really where we're getting at, because once we know our Ka, then we know our pKa. So step 3 would be then looking at the filling in of the ice table. So we have, our starting material, the caproic acid. We have as well then its conjugate, the caproate. And then we have hydronium ion. And we then have our initial, our change, and our equilibrium. So going back to the question, what information do we have here? Well, we do have a mass of caproic acid into 500 milliliters. So there would be an initial set of conditions for the caproic acid. We also know that the pH of the solution is 2.94, and that is giving us access to our hydronium ion at equilibrium. So with those two pieces of information, we actually, I think, have the ability to fill up completely the ice table. And to be honest, that's what we need to do, right? Because the only way that we can get at a Ka is if we know all the concentrations at equilibrium. So we have to do a little bit of work to get these values. So we would have to take, for instance, our 5.5 grams of the caproic acid. Right, we would have to get that into a concentration by first dividing by its molar mass of 116 grams. That's going to allow us to get to moles then of our caproic acid. And then we can divide by that volume that we were in, 0.5 liters of solution. So we're just doing a simple conversion to get out of mass and to get into moles, and then divide by our volume to get into molarity. And so we end up with a concentration of 0.0948 molar. And so that is going to be our initial concentration for the caproic acid. So plugging that in at the top, we have that particular value. There's no mention of initial conditions of our hydronium ion or the conjugate base caproic, so we would have to have, 0 molar there, which is then helping us with our understanding of change, that we would have to have positive change. We'd have to produce our products, but then we would lose our starting materials, and back to that reaction, they're all 1 to 1 to 1, so it's just minus X or plus X. We have an angle on X as well, because we can solve for our hydronium ion concentration at equilibrium by taking 10 to the minus pH. So we would take 10 to the pH of 2.94, so minus 2.94. That gives us a concentration of 1.15 times 10 to the negative third molar in terms of that hydronium ion concentration at equilibrium. So we have our value for the equilibrium of hydronium, and that's actually telling us then what our value of X is going to be. Right, it's going to be a positive 1.51 times 10 to the negative third, for both my products. So we're seeing that increase being synonymous. And then we would have minus that value for our caproic acid, our starting material. So we would have 0.0948 minus 1.15 times 10 to the negative third. So there are all of our equilibrium values. So now we can substitute, back into Ka and basically solve for Ka. But then from that Ka, then answer the question and get to our pKa. So our Ka was equal to those products over those starting materials. So just to remind us, we would have the caproate times our hydronium ion all over the caproic acid. And so going back up to that table, we would have 1.15 times 10 to the negative third for the concentrations of both our products, the caproate and the hydronium ion. And then we would have 0.0948 minus that value of change for our starting material, the caproic acid. And so we get a Ka then of 1.407 times 10 to the negative fifth. And then that allows us to solve for our pKa, which would just be the negative log of that Ka. And we get a pKa equal to 4.85. So that's an example of a weak acid, and also an example of now looking at the other side of the picture. We solved earlier. We knew the Ka, we got hydronium and got pH, and now in this example, we actually have all the pieces for the equilibrium concentrations, and that's allowing us now to solve for Ka, so both sides of the coin. And then just realizing that there's a connection between Ka and pKa, just like there's a connection between hydronium ion and pH. And so we can then go further and then solve for the actual pKa. The last example for strong acids, weak acids, strong bases, weak bases, we step it up a little bit higher here for this particular question by thinking about now, we've solved for K, whether that be Kc, Kp, Ka, or possibly Kb. We've already done that. We've also been able to solve for equilibrium concentrations using big K, Keq. But we've not yet been able to see an example where we might solve for the initial concentration. Usually we're given the initial, but what if we're not given the initial? And so that's what this last example looks at. So how many grams of methylamine has this as its structure? So we see that base idea with the nitrogen in its lone pair. So how many grams of methylamine has to be dissolved in 2.5 liters of aqueous solution, in order to prepare a solution with a pH of 12.2. The Kb for methylamine is 4.8 times 10 to the negative fourth. So there's our question. We want to figure out, basically initial conditions. How many grams of methylamine do I have to dissolve in 2.5 liters of solution to prepare the solution with a pH of 12.2? So we can keep reinforcing our methodology, right? We need to identify, and so we can think about, our structure, where we have, our amine base, or the idea that we have a Kb equal to 4.8 times 10 to the negative fourth. And so both of those are identifying this methylamine as a weak base. So with the weak base, that allows us to determine our reaction. This is going to be an equilibrium process. And again, that comes from the identification that it is actually weak. So now we can show that proton shuffle, but now it's going the other direction. Instead of the proton being given to water, in this case, it's going to be, water is going to be donating the proton. And that generates methyl ammonium, as well as then hydroxide. And so that is our Kb for the process. And so that allows us now to really realize the important players. We have the methyl ammonium and hydroxide as our products in the numerator, and then we have our methylamine in the denominator as our starting material, and that's equal to 4.8 times 10 to the negative fourth. So that allows us to get to the ice table. We have our starting material, the methylamine, as a player. Its conjugate acid, the methyl ammonium, and then the hydroxide. And so we have a set of initial, a change, and equilibrium. And so if we go back to the data that's given to us, right, they're really asking us, how many grams of the methylamine dissolved in 2.5 liters of aqueous solution. So this is really trying to figure out the initial concentration of the methylamine. We are given a pH, and that's always important because that's giving us hydronium ion at equilibrium. We've already used our Kb in the expression. So in terms of trying to figure this out, as far as our ice table goes, well, we would have an initial concentration of the methylamine. We just don't know what it is. We know there is one. We're trying to solve for it, but we just don't know what that concentration is, obviously. There is no mention of hydroxide or methyl ammonium initially, and that is allowing us then to again determine our change, which is going to be positive towards products and negative for our starting materials. We do have some information. We do have a pH equal to 12.2. And so from that, I can get to my pOH and then get to hydroxide at equilibrium. So that would be kind of the thought process for being able to fill out a good portion of the table, is that I can figure out my hydroxide ion concentration at equilibrium. Right, my pOH would be 14 minus my pH. So my pOH, would be 14 minus my 12.2, or equal to a value of 1.8. I can then get at my hydroxide ion concentration at equilibrium by taking 10 to the minus pOH. I did something very similar with hydronium ion and pH, and I can do the exact same thing with hydroxide ion and pOH. So I want to take 10 to the negative 1.8, and I get a value of 0.0158 molar, and that's my hydroxide concentration at equilibrium. So that's allowing me to plug that in really here, and that's now my X value that I want to take plus 0.0158 molar for the change, or minus that value. So that means my concentrations of my product are both the same as 0.158 molar, and then my starting material, which is what I'm looking for, would be that initial concentration minus the 0.0158 molar. So that concentration at equilibrium is what I'm plugging in there, which is then allowing me to determine the actual change that's occurring. So now we're at that fourth step. We can substitute back into our KB and basically solve for that concentration that we are looking for the methylamine initial. So our KB was equal to our products, the ammonium, methyl ammonium, and the hydroxide over our methylamine. We now start to plug everything in. We have our KB, which is the 4.8 times 10 to the negative fourth. That's equal to our concentrations of methyl ammonium and hydronium, which are the same as 0.0158 molar. And that would be all over then my initial concentration of the methylamine minus that 0.0158 molar. So that's plugging in all the values. And so we can then eventually, we can solve this process then via some, derivations here. So if we take our 4.8 times 10 to the negative fourth and bring over our denominator, we would end up with something like this, right? And that would equal 2.496 times 10 to the negative fourth. If we distribute, we get 4.8 times 10 to the negative fourth times that initial molarity minus then 7.584 times 10 to the negative 6. And so that's still equal to what we have on the right side. We want to collect like terms. So our 4.8 times 10 to the negative fourth times that molarity is equal to 2.572 times 10 to the negative fourth. And our molarity at the end is equal to 0.5358 molar. So that's the initial concentration that we actually have for the methylamine. And so now we can do a conversion to figure out our mass. We have 2.5 liters of the methylamine solution. If we multiply that by our molarity, we can get out of the solution and get into moles of our solute, the methylamine. And then if we multiply that by the molar mass, and methylamine weighs around 31 grams per mole, we can get our mass. And so we end up with 41.5 grams of methylamine will, produce a pH equal to 12.2 when diluted to 600 milliliters of solution. So there is our final answer after that last conversion out of moles and into grams. So there are a number of examples that we've done in this lecture about looking at strong acid, strong base calculations. We've also looked at a number of weak acid calculations on both sides, on the equilibrium concentration side as well as the Ka side of things. And then we've also done a base example here at the end, now looking at an initial set of conditions. So a lot of good examples here are talking about and reinforcing the methodology for solving calculations involving strong acids or bases, as well as weak acids or weak bases.